This is my first time in Slovenia. I think I should first kind of introduce myself. I hold a Bachelor's of Science in Physics from the State University of New York. I hold a Master's in Biomedical Engineering from Drexel University in Philadelphia. And I hold a PhD in Environmental Sciences from the New University of Lisbon. So just to give you some academic background, because I will be covering from noise to cells to health. So, and this is what gives me the right to do so. We will first talk about the agent of disease, which is infrasound and low-frequency noise. These are pressure waves that come through the air. They are not constant. They vary in time, in frequency. They vary in time, in amplitude. And pressure is a force per area. The World Health Organization, I have to get this straight. The World Health Organization calls noise inanimate mechanical forces. So basically noise or any pressure wave that comes through the air is an inanimate mechanical force, which you may or may not hear. So it's not as simple as one would like when we are talking about specifically low-frequency noise. What is the difference between low-frequency noise and the noise that we hear? Basically, it is the distance between the waves, between the peaks. Low-frequency noise has a very large distance, while high-frequency noise, which is what we hear, it's a very small distance. For example, at 3,000 hertz, we hear very well. The distance between the peaks at 3,000 hertz is around in the centimeter area. When we go down to the low frequency, 20 hertz is considered the limit of our hearing. In the low frequency, the distance is 17 meters. Rule of thumb is when you want to make a barrier, an acoustic barrier, the thickness of the barrier must be on the order of the wavelength. So if you want to protect against 20 hertz, you need a barrier of 17 meters. Okay, maybe you have special materials, 10 meters, that's still very big. And when you go down to 1 hertz, it's 343 meters. This is the problem with low-frequency noise. It penetrates into the buildings. It penetrates the earth. And this is why it is a problem for human health. We all know about radiation. Usually, the public is very aware of the radiation. We all know that in radiation, there is a very small section where we can see. But then we have ultraviolets, and we have X-rays, and we have gamma rays, and these we do not see, but they can affect our health. This is the same in acoustics. In acoustics, we have audible sounds, and then we have infrasound. We also have ultrasound. I and my team, we study the low frequency, so that which is audible but barely, and also the infrasound. Historically, we all know, since the time of the ancient Greeks, we all know that loud noise can make us deaf, can impair our hearing. So historically, we have tried to concentrate protection against noise in the area where we hear the best. So conversation area, which comes about to 500 hertz to about 10,000 hertz, this is where we concentrate all of the protection of noise hearing or too much noise exposure. As you can see, the hearing is always what is protected. The body is not. It is assumed wrongly by many that if you don't hear it, it won't hurt you. Okay? Well, we don't see X-rays either, and it hurts us. So the idea, it's unique in medicine, unique. The idea that we have to perceive the agent of disease for it to harm us, it's wrong. We don't see viruses. We don't see many things that are harmful to us. Why do we insist in noise that we must hear it for it to be harmful? This is not a good methodology, and we shall see there is evidence for this. This is an example. It's a movie of an environment near a wind farm. What you see here is the dBA measure. Notice it will never go over 40 dBAs in this example. But this is what is really there. This is what you hear, but this is what you are exposed to. And it is not being taken into account in hardly any legislation in the world, although Russia has infrasound legislation specifically for the cities. So there is somebody who knows something. Our team has been recently measuring, we have a new equipment, and we are now measuring noise with this dB linear. Notice at 1 hertz, the difference between what we measure and what is there is 0. At 10 hertz, the difference between what we measure and what is there is 0, etc., etc. This is the way we can scientifically quantify the agent of disease. We are not even quantifying it. We are not even acknowledging it is there. So for science, it's very important to get a number to find out how much is there. And you can do this with infrasound and low-frequency noise as long as you have a dB linear. Any measurement who says they are measuring infrasound and low-frequency noise and they give it to you in dBA units is scientifically invalid. In terms of biology, our cells respond differently to different frequencies. So the lung will respond to a frequency that is different from the liver. We have nothing against wind turbines. We have maybe as much against wind turbines as we have against airports, metros, public transportation, other industrial complexes. We study the effects of infrasound and low-frequency noise wherever they come from. This is the old way, or the way legislation demands that we measure noise, without wind turbines and with wind turbines rotating. Legislation looks at this only. This is dBA. This is the only thing that they will look at in terms of the noise. And here also, without wind turbines and with wind turbines, you can see in dBA, the difference is not so much. But you are exposed to a lot more acoustic energy with the wind turbines rotating than without. But this is not reflected by legislation, as you can see. Legislation looks at this red bar only and does not care about this gray bar, which reflects the acoustic energy that is actually present. This is the old way of doing things. We now have a new machine. Why is it important, this new machine? As you saw in the previous picture, it's like a photograph, stopped in time. Here, we have time from 0 to 600 seconds. It's 10 minutes. So what I am showing you here is 10 minutes of the acoustic environment without wind turbines and 10 minutes of the acoustic environment with wind turbines. Of course, the more yellow it gets, the higher the intensity, the higher the dBs. Notice what happens with the wind turbines. You have a clear pulse. It's clear. As it's yellow, it's not a continuous line. If it was continuous, you cannot get this information from data like this. There is no time factor. And we are finding out that the pulse, the time of the pulse, is important for the biological response. It is not just the frequency, it is not just how the amplitude, the dBs. It is also very important, the pulse code. That is important for biology.